Guys, welcome to another episode of CUDA Education. Today we are just going to do a quick overview of the compute ray tracing algorithm. Let us just begin. We're going to run the application and we're going to see what is what. So we're running the application. I'm running it on my I'm running it on my local on the integrated graphics card, the Intel graphics card associated with the CPU or close to the CPU, not the discrete graphics card. So I do it on purpose just because the frame rate is a little bit slower and we could actually see the calculations and stuff that's going on with the algorithm. Obviously, if I run it on my NVIDIA card, it would be a lot faster. But we're not concerned about speed. We're concerned about learning and understanding what's going on. So the purpose of this video is just for me to do an initial run through of the algorithm and to see where we stand with all of it. So let's just go through the algorithm, and see what we pick up, and then we will dive into. Yeah, we'll just start from the top, go down, and then we'll get into more details later. All right, so this is the compute shader based ray tracing example. So um, basically, what we're doing is we are computationally simulating ray tracing. So we're not using um, we're not using the ray tracing hardware on the GPU. So in the case of NVIDIA, that's the RTX series. There's ray tracing hardware on the GPU that deals with the acceleration structures and all of the things associated with ray tracing. So this particular example does not use that hardware. So that means that if, for example, you have a GTX card, a card that is not ray tracing capable, you still would be able to run the example because because this is not taking advantage of the ray tracing extension in Vulkan, which furthermore means that you're not trying to use the ray tracing hardware on the GPU. So you'll be able to run this, but you wouldn't be able to run all of these ray tracing examples if you don't have ray tracing hardware on your GPU. So for NVIDIA's case, it's the RTX series and later. GTX series and before that is not you're not able to run the ray tracing examples. However, you will be able to run this example. Okay, so this example implements a basic ray tracer with materials and reflections using a compute shader. Shader storage buffers are used to pass geometry information for spheres and planes to the compute shader. The compute shader then uses these as the scene geometry for ray tracing and outputs the results to a storage image. The graphics part of the sample then displays that image full screen, not to be confused with actual hardware accelerated ray tracing. So this is the part not to be confused with actual hardware accelerated ray tracing. This is the part where it's talking about it's not using the ray tracing hardware in your GPU, and it's not using the ray tracing extension in the Vulkan API in order to run this example. Okay, so if you have an older GPU, you still will be able to run this algorithm because it doesn't expect um, ray tracing hardware on your GPU. Okay, so that's pretty much it. So we have a class. The compute shader will store the ray traced output to a storage image. So basically, we're trying to build an image each frame or what have you. So we have a storage image, resources for the graphics part of the example. The graphics pipeline simply displays the compute shader output. Right, everything is done calculation wise, so all the graphics has to do, it simply displays the compute shader output. So the compute shader is sort of directing the ray traced output to a storage image. So the compute shader is like building the ray traced output to the storage image, and then the graphics pipeline just displays what the compute shader outputs, right? So we have all of the processing here. We have a strut, a graphic strut with descriptor set layout, pipeline layout, and this is all part of the graphics strut. Okay. Resources for the compute part of the example. Compute. Separate queue for compute commands. Queue family may differ from the one used for graphics, right? So we have to manage the the queue family stuff. I have extensive episodes on this specific conversation. The one queue family is graphics and compute, and then another queue family is dedicated compute. So depending on your specific hardware, we have to manage which queue family we're running compute on. Command pool, use a separate command pool. Queue family may differ from one used for graphics, right? So command pool is just, system resources dedicated to, eventually making the command buffer and all of that stuff. I have a whiteboard on the command pool and all that stuff. Um, and yeah, max concurrent frames, uh, array, max concurrent command buffers storing the dispatch commands and barriers. Okay, and then we have a fence, guys. You already know when we talk about fence in synchronization, we're talking about CPU to GPU synchronization. Um, Synchronize fence to avoid rewriting compute command buffer if still in use. So again, fences, VK fence, we're dealing with synchronization. Synchronize fence to avoid rewriting compute command buffer if still in use. So if we're currently executing or using a compute command buffer, we don't want to be um, trying to rewrite or update or modify that same command buffer while while we're using it. So we need to have a sort of a synchronization barrier to deal with that. The writing actually happens on the CPU side, but the execution of the command buffer is on the GPU side. So fences is CPU GPU synchronization. So we're not going to attempt to rewrite we're not going to attempt to rewrite the command buffer if it's being held up by the GPU and being executed by the GPU and all that stuff, right? So that's what this synchronization thing is about, this right here. All right, descriptor set layout, compute shader binding layout, descriptor set layout, pipeline layout of the compute pipeline. All right, and then the actual pipeline, compute ray tracing pipeline. Okay, so this is the compute pipeline. Um, yeah, uniform data compute. Okay, so compute shader uniform block. So we have a light position, aspect ratio, fog color. Um, we have stuff dealing with the camera. Um, Not sure what this is, linear algebra stuff. Um, but this is all part of the uniform data structure. Okay, so this is uniform data structure. Object properties for planes and spheres are passed via a shader storage buffer. Okay, so there's no vertex data. The compute shader calculates the primitives on the fly. So this is I believe this is dealing with procedural geometry. So the spheres, I know for the spheres are done just sort of mathematically. It's not like we input a mesh or any kind of structure or anything like that. It's just computed mathematically. So object storage buffer, um, uniform buffer object containing scene parameters. These need to be per frame in flight as CPU writes while GPU reads from it. Um, So buffer, uniform buffer, descriptor set. Let us get Okay, so right, this entire thing is compute. So going from here to here, all of this is compute, right? Right. Okay. Right. So all of this is compute. So this is resources for the compute part of the example. So all of this that we covered right here, all of this that we covered right here is for compute. Okay. Um, and that's that. Definitions for scene objects. The sample uses spheres and planes that are passed to the compute shader via a shader storage buffer. The compute shader uses the object type to select different calculations. So, um, scene object type, we have sphere is 0 and plane is 1. Now, let us actually play around with that for a second. So, we have our example right here. Let us see what happens if we change it around. Okay. And we get this for whatever it's worth. But we're not, yeah, we'll just leave that alone for now. Okay. So we have back to our original so scene object type. We'll have to investigate this, guys. We'll have to investigate this. So scene object type, sphere is 0, plane is 1. Spheres and planes are described by different properties. We use a union for this. Um, Position and radius, normal and distance. Um, Scene object, struct scene object. Diffuse specular ID object type. Due to alignment rules, we need to pad to make the element align at 16 bits. So yeah, this is sort of some kind of memory optimization in terms of how things are digested. Um, so I've seen this before. Um, yeah, I've seen this before somewhere. Don't remember exactly which program, but I've seen it before. Anyway, so that's your scene object strut, and then we have compute shader, ray tracing, timer, camera stuff. Then we have our destructor. Good housekeeping, guys. We have to destroy things after we use them, so that we're not slowly eating all of our system resources while the application is running. So yeah, this is just destructor destroying everything. Prepare storage image that is used to store the compute shader ray tracing output. So prepare storage image function. So use a smaller image on Android for performance reasons. Else we use this. Um, yeah. Get device properties for a requested texture format. Format properties, get physical device format properties. So we put in our physical device, our GPU, and we put in the format, and then we have a pointer to the format properties. That's what's outputted. Check if requested image format supports image storage operations required for storing pixel from the compute shader. So assert. This is a pretty strong thing. This is a strong thing that if it fails, it's a problem. But anyway, we optional tiling features. So we take our output from this function, which is this guy right here, the handle, and we test for optimal tiling features and VK format feature storage image bit. So we're testing against these two things to make sure they come back true, and if not, we assert. Um, Prepare blit target texture. So texture size, width, height. Um, yeah. So we have VK image create info. So we're creating now. Remember we're in the prepare storage image function. So we're, you know, setting up all of our image parameters, image type, format, extent, bitmap levels, array layers, samples, tiling, initial layout. Um, I hope to mess around with this stuff to see exactly what is what and how it all works. Image will be sampled in the fragment shader and used as storage target in the compute shader. Image will be sampled in the fragment shader and used as a storage target in the compute. Right, okay. Um, so, right, we have two flags here in terms of usage. Okay. And flag is 0. Memory allocate info. VK create image. Okay, so remember, guys, when we see lowercase vk, we know that we're talking about a very important function. So vk create image device, image creation info, which basically what this is doing is it's collapsing all of this information, into this null pointer storage image. So right. So I assume this will be our handle to what is created here. Um, I want to quickly go to definition. Okay, so this is right. So storage image was created here as a texture. And then we got to right, we got to here. So we're creating the handle. So dot image is basically the handle for what's created with vk create image. VK get image memory requirements. A lot size, memory type, index. Allocate memory. Bind image memory. Don't think I've really seen this before. VK bind image memory. Um, Layout command, Vulkan device create command buffer, image layout, set image layout. Add an initial release barrier to the graphics queue so that when the compute command buffer executes for the first time, it doesn't complain that a lack of a corresponding release to its acquire. So this is standard procedure. We've seen this many times before. Um, yeah, basically we have to do a special thing for initial conditions. So right, so add an initial release barrier. Okay, so right, this is trying to manage now, if the graphics and compute queue family is not the same. So if they're not the same, then we proceed. So image memory barrier, synchronization stuff. Um, we'll have to investigate this. We have a pipeline barrier. Pipeline barrier is a pretty strong synchronization barrier. Um, But notice that this is the lowercase vk. So lowercase vk cmd pipeline barrier. This is the handle for the result of this barrier. So image memory barrier. Okay. Um, flush command buffer, create sampler. Yeah, we'll have to figure out what all of this stuff is. Again, we have our lowercase vk create sampler, which we'll have to investigate. Um, what that's all about. I don't think I've seen this before. So this is specific to this compute ray tracing situation. Image view. I have a whiteboard that briefly talks about the cascade of all the things to create an image, but you have to have an image view in the mix. So we have VK, lowercase VK create image view. Kind of looking forward to investigating this algorithm because there's a lot of stuff that that's new here, that's not very is not used in a lot of the other examples I've ran through. So this will be an interesting one. Initialize a descriptor for later use. We'll see what that later use is about. Set up and fill the compute shader storage buffer containing object definitions for the ray traced scene. So prepare storage buffers. ID used for to identify objects by the ray tracing shader. So current ID is 0. Add some spheres to the scene. Lambda to simplify object creation. Um, I don't even want to mess around with this because I don't want to lose the video. So I'll just leave it. I'll just leave this as now. But this is an add sphere thing. Add plane. So I guess these are the parameters. I count 1, 2, 3. Okay, right. So I count 1, 2, 3 parameters here. So 1, 2, 3 parameters, and then 4. So 1, 2. Yeah, okay, I gotta investigate this because so it's 2 parameters here. All right, we'll have to investigate what this add sphere, how this add sphere works. But basically, we add 3 spheres. Um, room dimensions. Add plane, add plane, add plane, add plane. Storage buffer size. So we're copying data from the CPU to the GPU. So yeah, all of this right here. Staging buffer. We've seen this many times before. But we're moving. I do have a whiteboard on staging buffer. So if you guys want to search my channel for that, it would be a good idea to do so. Um, and then after we're done with the staging buffer, we destroy it because we don't need it to be living in the system if we're not using it anymore. Descriptor pool will be shared between graphics and compute. So we have our descriptor pool, and we're doing all of that. Prepare the graphics resources used to display the ray traced output of the compute shader. Hopefully this is simple because it's not much going on here. The graphics pipeline uses one set and one binding. Binding 0, storage image with ray traced output as a sampled image for displaying it. So yeah. Set layout bindings, descriptor layout, alloc info, VK update descriptor sets. Lowercase VK, guys, we know that means serious business. So we actually deal with it right here. We have our layout, VK create pipeline layout. We have our pipeline. Notice with pipelines, it's always a lot of parameters. So we have input assembly state, rasterization state, blend attachment state, color blend state, depth stencil state, viewport state, multi-sample state, dynamic state, enables, dynamic state. Yeah. And at the end of it all, we should get a lowercase vk function. Load shaders. So we have a vertex shader and our fragment shader. Actually, when we look at the shaders, we have three shaders. We have a ray tracing comp, we have a texture frag, and a texture.vert. So that's what these things here are referencing, right? These two guys. Empty input state, pipeline create info. So we have our pipeline create info, and then we have our lowercase vk create graphics pipeline. So all of that work is for this guy right here. Okay. And we have a vk check result just to make sure everything ran fine, or else it will throw an error. So all of this work is literally for this, right? This pipeline create info and pipeline cache and all. Well,